The universe likes to even out differences. It likes everything to be the same. So the laws of physics frequently are designed to eliminate differences between things. So you put a hot thing next to a cold thing, they'll both end up reaching in the middle about the same temperature. That's where the expression nature abhors a vacuum comes from. If you have an area with a whole bunch of stuff right next to an area with not much stuff, their stuff is going to leak into the other area until there's equal amounts of stuff in each area. So these differences are called gradients. It's differences in some quantity from one area to another. It's why so many things go on in our world. So, for example, hurricanes are just a way of trying to help balance the energy difference or eliminate the energy difference between the warm equatorial regions and the cold polar regions. Hurricanes are a mechanism of transferring energy from the warm equator northwards towards the poles. So, heat transfer, the uh, transfer of thermal energy from one location to another location, is the topic of this part of this module. And there are basically three different mechanisms that we're going to be talking about for heat transfer: conduction, convection, and radiation. So for thermal energy to get from one thing to another thing, or from one place to another place, it's going to happen through one of these three mechanisms. Conduction, we're very familiar with. That is the process that happens when something is literally in contact with another thing. So you touch something that's hot. That hot property means that the molecules and atoms of that hot thing are moving very quickly. And when you touch it, the ones that are uh, in contact with your skin are carrying a lot of kinetic energy and making contact with the atoms and molecules in your skin and giving them some of that kinetic energy. Yeah, so it's not physical contact, it's interactions through the electromagnetic forces we've discussed earlier via the electrons in those atoms and molecules. But we can think of it in a simple sort of billiard ball sense. A hot object has got a whole bunch of billiard balls in it, the atoms and molecules that are moving very quickly. And if you go touch them, they are bouncing into the billiard balls that make up you and cause them to vibrate more quickly, and some of that energy is transferred. That's the transfer mechanism of conduction. So that's what happens when you cook on a stovetop. It's also what happens when it's a hot day outside and the uh, heat is conducted through the walls of your home just by the hot air. Literally, the molecules in that hot air are moving more quickly. They heat up through collisions with the atoms and molecules in the walls and make them warmer, which then heats up the air on the inside of the house. So it's direct contact. Conduction involves direct contact between two objects. And we can quantify how rapidly energy is conducted via conduction with a property of a material called its thermal conductivity, which is represented by a little letter K. And if something's got a high thermal conductivity, that means that it will rapidly conduct energy from through it. So if I take, for example, in the slide here, we see values, for example, steel has a thermal conductivity of 46 watts per meter Kelvin. And what that means is that uh, if there's a 1 Kelvin temperature difference across 1 meter of steel, 46 joules of energy will flow through that steel per second. On the other hand, if I had fiberglass, which is a material used for insulation, which has a thermal conductivity of only 0.042 watts per meter per Kelvin, that means if I had a 1 meter thick layer of fiberglass and it's 1 Kelvin temperature difference, only 0.042 joules of energy will flow through that fiberglass per second. Notice that that thermal conductivity means that if I have a 10 times bigger temperature difference, I'll have a 10 times faster flow of energy. Watts is power, it's flow of energy. So a small number for thermal conductivity would make something a good insulator. and a large number means it's a good conductor of heat. So you would not want to use, for example, based on the numbers that we see here, an aluminum spoon to stir your pasta on the stove because it will very rapidly conduct thermal energy from the boiling water through that aluminum into your hand because of that high thermal conductivity. Now, we can calculate the total amount of heat that flows through something via conductivity using the equation shown here, and you'll have some homework that requires you to do some calculations like this, so take a look at the example problems. But the heat flow in watts is equal to the thermal conductivity K times the temperature difference, the hot side minus the cold side temperature, and that's a temperature difference, uh, divided by the thickness of that insulator and then multiplied by A, which is the area of it. So that tells you the total amount of heat flowing through some material as illustrated in this example here. And the best way to get a handle for this is to actually work through some example problems. And so you can follow those examples and then do them in the homework. When you're shopping for insulation, the usual quantity that is given is not the conductivity of a material, but something that is a measure of how good an insulator it is. And so that's inversely proportional to the conductivity. It's this value called an R value, and R is equal to D over K, where K is the conductivity. Remember, a big value of K means a large amount of energy is conducted quickly. So if K is in the denominator, that means not much energy is conducted quickly, and that's what you want in an insulator. And then D is just the thickness of it. The thicker it is, the longer it takes for that energy to go through. So a large R value means it's a good insulator. And the reason we use that, or one reason we use the R value, is because we can add R values up for different uh, things. If we have a layer of insulation, then a layer of wood, then another layer of insulation, then a layer of air, and then a layer of drywall, we can just add the R values up for all of those different things and get the total R value for that whole wall. So it's very easy mathematically to figure out the R value of something that's got lots of different stuff going on. So the table here shows some typical R values. And again, it depends on the thickness. So fiberglass, it's 3.5 inches thick, may have an R value of 12. 5.5 inches thick has an R value of 19. That's just because it's thicker. If it was 11 inches thick, the R value would be twice as big as the 5.5 inch. So 2 times 19 is 38. So it just adds up that way. And that's what's illustrated in this slide here. Now, the second of the three types of energy transfer we're going to talk about is convection. And convection, remember, conduction is direct contact of two things. Here's a hot thing, here's a cold thing. They have to touch, then some of the energy gets transferred at that sort of molecular level between the hot thing and the cold thing. Convection is the bulk movement of a warm thing to a cold area where it then releases its thermal energy through conduction or radiation at that cold location. So that energy is really carried by the motion of a warm thing. So examples of convection are clouds. You see clouds forming in Florida. That is warm, moist air near the surface that's heated up because sunlight is absorbed at the surface and heats the air at the surface. That air expands. When it expands, it becomes buoyant compared to the surrounding air, and it rises. And so it's carrying thermal energy because it's warmer, and it's carrying that thermal energy up to a higher altitude, where other processes then transfer that thermal energy to the surrounding air. And I've got a demo to show what that looks like. But the slide here is just showing that convection is very important for transferring energy in the Earth's lower atmosphere, in the troposphere, the lowest layer of the atmosphere. Convection is the energy transport mechanism in the Earth's atmosphere. In other parts of the atmosphere, it's other mechanisms, as we will talk about. There are global convection, not just local to form clouds. The figure here shows that if we look at the planet as a whole, of course, the sun is heating the equatorial regions more directly than the polar regions. And so the air over the equator is generally going to be warmer than the air at higher latitudes. So that causes that air to rise. So if you take a look at the arrows right above the equator, they're going up. You have these the arrows are pointing towards the equator, then they go up. That's the rising air at the equator. That air rises. It can't just sink straight back down after it's cooled off because there's air coming up beneath it. So it has to move north or south, and eventually then it sinks. There are three of these big cells of convecting air in the Earth. This is global scale convection, not the local convection that gives us thunderstorms here in Florida. This is global scale convection. And as it happens, there are three of these big convecting cells that are called Hadley cells in each hemisphere of the Earth. 6 total, 3 in the north, 3 in the south. The reason there are 6 has to do with the size of the Earth and how fast it's rotating. Other planets, such as Jupiter, have more because they're rotating more quickly. These global convection cells are going to be very important when we're talking about wind power later in the semester. Another example of convection is just boiling water. So put a pot of water or soup on the stove. You heat the bottom of the stove by conduction if you're, unless it's well, you're heating it by conduction unless it's a radiative stove. So the stove is in contact with the bottom of the pan, it heats it by conduction. Then the pan is in contact with the water at the bottom of the pan, so that's heating it by conduction. And then that water at the bottom gets warmer, it expands. Because it's expanding, it's buoyant, it's less dense, so it floats to the top. So then you have a very rapid transport of energy from the bottom of the pan to the top. That is convection. It cools off at the top by giving its energy out to the air via conduction and sinks, and more warm water is coming up beneath it. So those are some of the examples that you have of convection. And the final energy transfer or heat transfer process that we want to talk about is radiative transfer. And this is ultimately what we need to understand climate change on the Earth, because the Earth can't conduct energy to space because space is a vacuum. There's no stuff to take the energy away. And for the same reason, it can't convect energy to space because there's no stuff there. We don't lose if the atmosphere just left and went off into space, it would carry some energy with it. But fortunately, the atmosphere is staying on the Earth. So how does energy leave the Earth? Energy is coming into the Earth from the sun. If we didn't get rid of energy at the same rate that it's coming in, the planet would be getting hotter and hotter and hotter indefinitely. And so for the Earth to be in energy equilibrium, as much energy has to be leaving as it's coming in. And the only way for energy to leave the planet, ultimately leave the planet, is through radiation, through light. All warm, dense objects radiate light. This is called thermal emission. You're doing it, I'm doing it, the walls are doing it, the book is doing it, the planet is doing it. Anything that is not an absolute zero and is a dense object that you can't see through is radiating what's called a thermal emission spectrum. It's radiating light at all wavelengths, and the amount of energy carried by that light is given by this scary looking equation here. But the important thing to notice about this equation, don't need to worry about anything except that temperature to the 4th power on the right hand side. So this says that the amount of energy carried away from an object by radiation is proportional to the temperature of that object to the 4th power. So it's very, very sensitive to the temperature of the object. If I increase the temperature of an object a little bit, then it's going to be radiating much more energy away. There's another aspect of the radiation of thermal radiation, and that is that the hotter the object, the shorter the wavelength of light that it is mostly radiating in. So the sun, the radiation that we're getting from the sun, is coming from a part of the sun that's at about 6,000 Kelvin. And that temperature leads to most of the radiation from the sun being in visible light, the light that we see with our eyes, which has a wavelength of about a half a micron, which is about 1/2 of 1% of the thickness of a human hair. For those of you fortunate enough to have hair, those were the days. The Earth is about 300 Kelvin, so about 1/20th the temperature of the sun, and that means that most of the light that's radiated from the Earth is about 20 times longer than the light that's radiated from the sun. And that's light that's invisible to us. It's called infrared radiation. And so we can't see it, but that is how the energy leaves the Earth ultimately, is from infrared radiation. And we can build instruments to detect that radiation. And of course, that radiation interacts with things. And as we will see, certain molecules preferentially absorb infrared radiation, such as water vapor, methane, carbon dioxide, and others, even though they're transparent to the visible light that's coming in from the sun. So those are the three main mechanisms for energy transfer. Take a look at the demonstrations and the example problems.